No. Okay. Okay, welcome everyone. I'm very excited to announce our very first seminar of this semester, and I'm I have the pleasure of presenting you Bernardita Ried Guachalla, who made her bachelor's and master's here in the University of Chile in our cosmology group. She's an ex-member of the group, and now she's a PhD candidate in Stanford. And today she's going to talk to us about the velocity reconstruction for kinematic Sunyaev-Zel'dovich effect. So take it away whenever you're ready.
Thank you.
Thank you.
Thank you so much for having me again. It's a great honor always to be back home. I'm really excited to talk about a challenge that is currently spanning different areas, not only in cosmology, but also in astrophysics. And in particular, it's revealing where is more or less 90% of the ordinary matter of our universe, in particular the so-called variants, that otherwise we miss in these galaxy surveys. In other words, these huge maps that we have reconstructed using tons and tons of galaxies. And because of that, we are missing a lot of information, in particular from particles that are spread out from where galaxies and clusters are, and I'll explain that in a second. The fact that we don't know exactly where they are, this is the so-called the missing variant problem. And I'm really excited to show you how you can use different cosmological proofs to actually constrain that. In particular, something called the cosmic microwave background that I'm pretty sure most of you have heard before. And also the large scale structure of the universe. And this is actually a really nice simulation from the Abacusanic group. Sorry, the illustrious simulation. Yeah, I'm mixing two names. But as I said, understanding where they are. So I'm gonna show you what I've been partially part of my PhD work. And in particular, I've been working on how to reconstruct the velocities of galaxies in the context of the Sunyaev-Zel'dovich effect that I'll also explain in a second. So reconstructing velocities, in particular, we test them in simulations. This is crucial for measuring the Sunyaev-Zel'dovich effect and therefore to measure where the gas is. So as an introduction, I would like to start with, let's see if I can move this. Okay, great. So you probably have seen this image before, or a small diagram of the history of the universe in which we have two main components. The first one is the cosmic microwave background, the afterglow and first light ever emitted after this hot Big Bang, more or less 380,000 years after that moment. And then we also have, let me take that out before. Okay. Oops. Back here. Okay, and the other pillar of cosmology in the context of understanding where the missing gas is the large scale structure. These two, okay, so I said this is the CMB or the cosmic microwave background. This is the first light ever emitted in our universe. And in the other side, the large scale structure, it's mainly the distribution of galaxies in these matter halos that then they group in this cosmic wave structure that you probably have seen. Sorry, here. And there's a lot of physics that we can learn if we really understand where the matter is distributed in the universe. For example, the first question I'm personally excited about, and I'm pretty sure a lot of you are too, is what is dark matter? Dark matter is this hypothetical type of matter that corresponds more or less to 85% of the matter content of our universe. And it does not seem to interact with light. In other words, it does not absorb light, it does not emit, but we know it's there because of its gravitational effect on surrounding galaxies. So for example, in here, I'm showing you how it would be distributed in a cluster of galaxies from a simulation. And it does affect the large scale structure. So in the summary, understanding large scale structure tells us about dark matter. Another thing you can learn from large scale structure is the distribution or how dark energy changes and evolves. So the dark energy is this well, we have Mario here, an expert on dark energy, but so you can ask him more questions. But mainly it's the fact that the universe we've seen that tends to expand even time faster and faster. So in here I'm just showing the expansion speed increase with time. And it does impact the large constructor too, because we're finding that really large scales, everything's moving away from everything. So that would be a second really nice physics that we can learn from large constructor, from understanding where galaxies are located in the universe. And finally, another interesting scientific question we can answer is the mass of neutrinos. So neutrinos are the second most abundant particles in the universe, and we know they are massive, but one of the biggest questions right now out there in physics is what is the mass of them? And if you actually run simulations and follow the theory that we do have for lambda CDM model or a universe that has expansion and dark matter, you can see, depending on the mass they have, they can impact the large constructor. And this is also a simulation. And therefore, understanding the large constructor tells us a lot about physics. And this is a great moment to do it, because we are reaching an epoch in the history of cosmology that we have great experiments. So this is a timeline that is not updated with many things that happened in the last 5 years, more or less. But I want to highlight that in here I'm showing two types of experiments that we call them surveys. In blue, light blue, we have, oh my God, you can't see, right? Images, sorry, the line is a bit bad here. But photometric surveys, therefore, mainly surveys of galaxies that are taking kind of photographs. It's more complicated than that, but you miss some of the 3D information. But still, they're really useful because you can get a lot of galaxies. And also there are many exciting experiments coming from the spectroscopic world. In other words, you can measure the 3D distribution of the large constructor. And as I said, it's a great moment because we're having these huge experiments, and luckily, some of them are happening here in Chile, and I'm also part of some of them. And I want to highlight two. The first one is the Rubin Observatory. So you're all in here, part of a Chilean institution, and if you do not know, you can join these collaborations and be part of the group of people that are going to be leading and using this large constructor. Sorry, I'm probably moving. Where's the camera? Here. So you're going to be probably part of the group of people doing the research. For 10 years, Rubin will be taking pictures of a changing sky, mapping it in more or less 3 or 4 nights completely with an unprecedented precision. It's a huge telescope, 8.4 meters for its diameter, and it's huge. And as I said, you can join this amazing group of people that are working on that. In particular, you can join the Dark Energy Science Collaboration, which is a group of people doing more cosmology here. But as I said, it's a lot of data, a lot of great science that does not only span the area of cosmology, but also astrophysics in general. Another great experiment that I'm also part of is the Dark Energy spectroscopic instrument. It's hard, it's easy to mix the names, but this is also an amazing experiment, a huge spectrograph with fibers that takes 5 spectra in every exposure, and it allows us to map the universe in 3D, so it can span 11 billion years of history of the universe. And the goal is also to understand dark energy. And this, actually, if you have ever seen Cerro Tololo, the 4-meter telescope, this is pretty similar. Actually, they were built at the same time. This one is located in Arizona, near Tucson, and they're pretty similar, actually. So it's really exciting. And again, a lot of people also from the cosmology world doing great science with this. But even though we have great data, there is still a key obstacle in order to get the scientific questions I showed before answered. And it's the fact that we're missing information, especially in the smaller scales. So the key challenge, one of the key challenges we're facing is the fact that when you see galaxies in a survey, you're observing more or less, well, you're only observing the galaxies themselves, or in other words, you're seeing the starlight of those galaxies. And if you count, okay, from the total amount of regular matter that is there in the universe, how much of them correspond to, the matter inside of stars. And if you do that calculation using previous cosmological results, more or less 10% of the baryons are inside of stars. So the question is, where is the rest of this regular matter? That challenge is called the missing baryons, because we know they're spread way farther away from galaxies. So in here, I'm showing the cluster simulation. This is the starlight we would see from a telescope. And then the second part is the gas from this particular simulation. The gas is usually spread out in astrophysical scales. So when you go and see a galaxy, the galaxy might have, for example, AGN, an active galactic nuclei with a huge black hole accreting material out, and inside, and it's a lot of chaos. You can have also supernovae ejecting material. So if we were be able to understand and localize those baryons, for example, we would be able to determine a lot of astrophysics. So as I said, through the galaxy evolution and formation, there's a lot of gas spread out, and understanding that process with an unprecedented precision is great. But also from the perspective of cosmology, it's important because if you probably have seen recent results, we have reached a lot of information, and we understand the distribution of the large constructor now in really smaller scales. And therefore, we're reaching the moment or the point of cosmology that the distribution of this gas is relevant because it can impact the distribution of the large constructor. So for example, if you're interested in weak lensing, where the baryons are at this regime might impact your results. So in other words, we need to understand where that gas or dust is in particular. Okay, so this is a key limiting factor at the large constructor study. What can we do? So I'm gonna skip this one, sorry. Yeah, so maybe we can use the CMB as a backlight. So going back to this figure I showed you at the beginning, we have the cosmic microwave background. If I said CMB, I mean the cosmic microwave background, by the way. And then we have the large constructor, and then there's us. We have our telescopes. And if we happen to detect photons from the CMB, this must travel through the large constructor, because they were emitted much before on time. But these photons do not travel freely. They might interact with the foreground. For example, they can get length. So the first arrow in here, I'm showing you how this is, of course, my draw. Okay, but what you will have is that you can have some lensing, and that's a whole group of people are working on this, and it's an amazing work they have done. But what can also happen is that you have a CMB photon, and it can scatter with one of the free electrons of this gas surrounding galaxies. So again, if I say gas, I mean all the baryons, and for cosmologists, electrons are considered baryons. So it's what we do. So if we are actually able to understand this with unprecedented precision, we can actually determine which of these photons are either lensed or scattered. And this is also a great moment to do it, because we have reached a great resolution on experiments on the CMB world. So another timeline. We have a lot of CMB experiments that allows us to understand that, and lucky enough, many of them are in the, as we say, the best country of Chile. Some of them are ACT. Also, we have Simon's Observatory and CMBS4. So the Chilean flags are the ones that correspond to Chile, and I'm currently part of ACT. And then the other group of great CMB experiments, ground-based, are the ones located in the South Pole. There are more experiments out there, and I think Claudia also can probably give a talk in the future about other experiments that also help us to understand the CMB in really smaller scale. with that being said, I just want to highlight I'm part of ACT, so the Atacama Cosmology Telescope. This was a 6-meter diameter telescope that was in Cerro Toco, really close to Alma, so it's more than 5 kilometers over the level of the sea, and it made one of the biggest CMB maps with one of the highest resolutions. And a lot of people use this to understand also the large constructor distribution because there's this interaction. And sadly, this telescope is no longer out there. They took it out. But again, more experiments are gonna come, so exciting times. As I said, we can have CMB photons interacting with the free electrons of the large constructor. So let's say you have your telescope or your antenna, because in the microwave world, people use antennas rather than telescopes. And you might have a CMB photon traveling and interacting with the electrons, free electrons from this cluster or group of galaxies or even a galaxy. And this might change their frequency. This effect is called the kinematic Sunyaev-Zel'dovich effect because two great scientists from Russia, worked on this theoretically back in the 60s. And so what could happen is that the frequency of the CMB photons, so usually people refer to the CMB photons as a temperature, and the change of temperature with respect to the CMB must be proportional to 2 quantities. So the first one is the number density of electrons, which makes sense. If I have more and more electrons, I will have more scattering happening. And then on the velocity of the gas. So CMB photons are usually low energetic photons. So they scatter through an inverse Compton effect with high energetic electrons. So we need to have electrons that have a lot of energy with respect to the CMB photons. So one way of giving them enough energy to be able to inverse Compton interact is to give them a bulk velocity or bulk motion. So if my galaxy or cluster is moving along the line of sight, this effect might happen. Yes, so this is the velocity along the line of sight. So again, if I have an object that is moving away from me or towards me, the CMB photon will interact because it's low energy. The electrons of this gas or the surrounding gas of this cluster or galaxy will have a lot of kinetic energy with respect to the CMB. There'll be this inverse Compton scatter, and then depending on the direction of this velocity, they might change their frequency, and that's what we observe. And so what is important with this relationship is that you have a change on temperature. You can relate that to the distribution of electrons out there, and you can link them to the velocity of the galaxies or clusters. And importantly, understanding where these electrons are could help us to overcome the missing barons problem. And also, this is in another scope, but understanding the velocity along the line of sight could also help us to understand the growth of structure, because galaxies that are moving with higher velocities and in voids or in different parts of the large constructor also tell us about early conditions. And as we were discussing yesterday with Colipi, you can use this also to, for example, constrain FNL. So people doing inflation, you can dream with this. So it's great. But going back to this effect that I'll call the KSZ, instead of calling it kinematic Sunyaev-Zel'dovich, tells us, as I said, about the circumgalactic gas. So if you can measure this quantity and you can estimate the velocity, you can constrain the number density of electrons. And that's what, for example, people have done, not only in clusters. So clusters are great because they're huge, they're massive. This is really easy to detect on a CMB, but people were wondering, can we do it in galaxies? So back in the 2020, Emmanuel Chan and Simone Ferraro and others measure this. So this is one of the first measurements on galaxies on how much the gas is extended. I will explain in a second how they did it. But I want to highlight that this yellow blob in the middle corresponds to the gas that is really, really extended. And if you actually observe one pixel, you will see a galaxy. So for you to have an idea, what they found is the gas is way more extended, even more extended than the dark matter halo. So we're talking about, for example, for a redshift 0.5 or 0.7, 2-3 megaparsecs. It's a lot. It's way more than the Viram. So the thing is that the processes inside of galaxies seem to be really energetic and throwing a lot of gas outside. But importantly, if we want to measure this, we need to have a good constraint on the velocities. So my first work for my PhD was to understand how we can constrain velocities looking forward to measure this. So I'm going to take a little pause and just wrap up what is the motivation of my work. So if we really want to take the best advantage of these large-scale structure experiments, we need to localize these missing variants in order to understand dark matter, dark energy, and neutrinos. And this is a great moment to do it because we have great experiments. But also, there's also great experiments from the CMB perspective, in which we will be able to measure, for example, this effect, the KSZ effect. But we need to have a good reconstruction of of these velocities, because a priori, when you see the galaxies out there, you can't just derive the velocity easily. And just to be sure, I don't mean the velocity with the expansion. I'm talking about the so-called peculiar velocity, so velocities that go beyond expansion, because also the CMB is traveling through a universe that is expanding. So it's the peculiar velocities. And especially in this new era of huge galaxy surveys. So is there any question? I'm gonna drink some water. I'll give you a second. Oh, I killed it. Okay, I killed it. It's there. Okay, it's there. If not, I'm gonna start jumping directly to my work. So how do we detect the KSZ? Okay. So this is a CMB map. This is from the Planck collaboration. But I'm not gonna be using this, but just for you to have an idea. So if you naively go to your CMB map, so it's 2 angles, 2 dimensions, and you locate the galaxies from your survey, like this, and you make cutouts of them, you can stack them. But if you do that, you won't get any KSZ signal. Because as I said, you need to take into account the velocities. So what you can do is to do the same thing. Again, go to your galaxies, make cutouts, but when you stack one over each other, you can weight by their peculiar velocities along the line of sight. That, if you do that and stack an average over all your galaxies, will give you an idea of what would be the shape of your gas around galaxies that hopefully are from the same type. And if you do that, you actually get a signal. And this is what my advisor, Emmanuel Chan and Simone Ferraro, did back in 2020, using EBOS galaxies, so galaxies from a spectroscopic survey, overlapping a previous ACT map. And so what they did again was to stack the CMB map on the galaxy's positions and weight by the velocities along the line of sight. And this gives you a profile. And you might say, well, but it's not well defined. You have these like blue parts, more green parts. So what happened is that when you're stacking on these regimes, you might have large contamination from the CMB primer and anisotropies. But this was one of the first time they did it. So actually, this is easy to overcome if you have more and more galaxies, which is something that's slowly happening. And I'm currently leading one of these measurements using DESI data. And as I said, at that time, they used this data, but they also were not as sure that they needed to estimate the velocities, and they did it in a way that it works, but they were not sure of details. So my first work was to understand how they were able to reconstruct velocities. So how do we reconstruct velocities in cosmology? There are many ways, but one of the simplest, and this is one of the nice parts of this work, is that we use the continuity equation. So you probably have, all of you have physics degrees, if I'm not wrong, and you probably all have played with continuity equation, fluids, and so on. And in other words, you have probably constrained mass conservation in your problems. And if you do that, and also consider a linear approximation to make this even simpler, you can get this following equation. So this is the gradient of the velocity. It's proportional to, let's forget about these 4 parameters, but just let's see this one. This is the overdensity of galaxies. So in other words, if you have your large constructor and you have an overdensity here, more mass, more galaxies, it's more likely that an object in here will like to infall in this overdensity because of gravity. So if you see this, if you use this equation and solve it, you can get that velocity field. So what we find in here is it's a simplification of the true velocity field, but it actually works pretty well in the sense that it captures this main idea. And so this equation is the gradient of the velocity. So in other words, if you make like a closed surface on these overdensities, you're saying that objects that are perpendicular to that surface, and then the negative is falling, is proportional to the overdensity of galaxies. So this is a way of quantifying densities in cosmology. Then you have 3 other parameters in here. This is the scale factor, this is the Hubble parameter, and the growth factor. So these 3 parameters are related in cosmology, and they tell us about expansion of the universe, also given the contents that you will have, and also the growth of the structure itself. And then this B parameter is just the linear bias of galaxies with respect to matter. So it's mainly parameters. And if you think of this is really simple from the perspective of physics. We actually don't use this equation. We do add something called Ricci space distortions. And that's mainly, in a small sentence, the Ricci space distortions are the effects of when you observe in a survey, if objects have peculiar velocities, you get like a Doppler shift, and the redshift will actually not be exactly the one. There'll be an error. And also that tells you a lot about physics too. So we can solve this equation, and in particular, what my advisor did and what I'm currently doing is to reconstruct it in 4 steps. So first, when you have a survey, you have 2 angles and a distance or a redshift. If you convert that into 3D coordinates, so x, y, z, then you can smooth it. So that's the second step. So first convert it to 3D coordinates, and then from these 3D coordinates, you can get a density field through a smoothing scale. And then if you do that, you get a smooth distribution, like a continuous one. So remember, galaxies are like points out in space, so you get a continuous field. You can use this equation that I showed you before. You can solve it. You can easily solve it in Fourier space, and you can just get an estimate of the velocities, and then evaluate the velocities at the position of galaxies, and you can get a not perfect but pretty close velocity estimation. So in this work, using this method, we wondered the following questions. How does this reconstruction change when you want to reconstruct, for example, velocities along with respect to across the line of sight? So galaxies might be moving like in this direction, like diagonal towards you. So that means you have 3D velocities. So how this changes when you have velocities along the line of sight and across. In the KSZ world, we care about the along line of sight, but other people care about the across for other interesting science too. Another question, sorry, is what can we improve from previous implementations of this method? And finally, which variables that I showed you before could impact the reconstruction? So we did this with my group. So they're great people. If you see them, please say hi. Boyana Hadiskia, Simone Ferraro, and Emmanuel Sean. Boyana and Simone are working on Berkeley, so they're neighbors from us. And Emmanuel is my advisor. And we had these 2 works in which I led a more like study in a simple box. So in order to understand how good are we on reconstructing velocities, we actually need the true velocities. In other words, we need simulations. Simulations, you can have a lot of galaxies, know where they're moving, and then when you reconstruct their velocities, you can compare and say, yes, this is good, or no, this is bad. So here I'm showing you a 2 gigaparsec length dark matter simulation. This is part of the Abacus Summit group, in which the blue colors would correspond to velocities towards us and red away from us. Every point in here corresponds to a galaxy. And I'm showing both the true velocity and the one we reconstruct with the equation I showed you before. So in my work, I used this box for a fixed redshift and studied effects such as redshift space distortions, photoseeds, and so on and so forth. And my colleague Borjana Hadiska studied this in a more realistic scenario. Because in reality, you are not going to have a box back in the universe. You're going to have a light cone, right? And I want to also highlight that velocities along the line of sight correspond to the ones from this direction and across the line of sight from this. And as you can see, the large scale velocity components are really well constrained. If you see this with detail, you can see that there's some gray areas. Those are velocities that probably were not well estimated because those correspond to small scales. And as I said, this method has a linear approximation, so we lose small scales, but we do have a lot of information in the larger scales. So you might say, okay, I'm gonna jump off into simulation because of time, but you can say, okay, Bernie, your figure looks nice, but we're doing physics, we want numbers. Okay, how do we evaluate how good this method is? Well, we use the correlation coefficient. So the correlation coefficient is the covariance between two quantities and the standard deviation of each of those. So in other words, we do have access to the true velocities. We reconstruct them and we can compare them. We can get their covariance and then the standard deviation, object by object. And then we can get an overall estimate of this. And why this turned off? Okay, it's back. Why we do this? Well, because if you actually go and read about the method that I showed you on how to detect the KSZ, this is proportional to the correlation coefficient of how good we are on reconstructing velocities. In other words, when we are measuring this kinematic Sunyaev-Zel'dovich through a stacking, weighting by velocities, if our velocities are not that good, the signal to noise ratio, or the signal with respect to the general noise is going to be worse if the velocity reconstruction is worse. And how? Like this. The correlation coefficient is proportional to the signal to noise ratio, because if you have a complete correlated, so if your velocities are completely correlated with your estimate, you're going to have a correlation coefficient equal to 1. If they're completely uncorrelated, this is going to be negative. And if there's no correlation at all, it's like random, you're going to get 0. In other words, 0 signal to noise. And also, it will be proportional to the square root of number of galaxies. So if you have more and more galaxies, also your signal will be enhanced. With that being said, I'm going to jump to the key results of my work, but I'm going to give a second pause to see if there's any question.
I have some, I don't know if I heard correctly, but did you say that the simulation was dark matter? It's not.
Yeah. Yeah, so let me explain you why. Because you were like, where are the galaxies, right?
Where is the gas?
Yeah, so we have n-body simulations. We use an HOD to paint galaxies over them. So it's if there's a really massive halo, we assign a galaxy with certain probability, following the DESI requirements. Yeah, I've realized I didn't say that. And we do have access to the velocities we paint over them, but also to the velocities of the host halos. So we have 2 types of velocities. And those do not have any gas. but we are only interested in understanding the velocities because this is simulations. It's just to test the method of the velocities.
But I thought that when you introduced this kinematic
Mhm.
Sunyaev-Zel'dovich effect, you were referring to the velocity of the gas.
Yes.
In the CMB photo with the scatter of.
Yes. Yes. So our big assumption is that, and this is something we're trying to learn more, is that the bulk velocity of galaxies, like the gas will also move with the bulk velocity. So in principle, it's true. It's probably not perfect. And I'm interested in understanding that effect more. But if you think of it, we're talking about really large scale motion. And if all galaxies are moving, the gas is probably gonna move too. There might be details, of course, and that's when astrophysics of galaxies enter more. But our assumption is that it moves with the gas. And we get detection, so it's there.
You would use the aerodynamic simulations where you have the gas.
Yes.
Have you thought about that?
The problem with that gas is that it's tuned with we use the results from the KSZ to tune those results. Something I didn't show because I was like, maybe I don't have much time, but let me show you something. I jumped that slide. This. So this is the power spectrum suppression from weak lensing using different simulations, hydrodynamical simulations. And what I want to show you, when you see small scales, the difference on the gas distribution can be more than 30% on the suppression of the power spectrum. In other words, simulations they can't constrain this regime really well. Either because it's like, okay, I'm gonna add a bit more of supernovae here or a bit of more black hole here, and they need more data to constrain actually their results. So measuring the KSZ, which is real data, can tune their simulations to reduce that difference. And even in smaller scales, this can diverge. So if you have a cooling system in your galaxy, you will have, instead of a suppression, like an enhaze. And then if you have gas expelled, it will change. So simulations, we don't want to use hydrode seams to measure KSZ. We want to use KSZ to tune hydrodynamical simulations.
What would be the quantity you're constraining?
Scales?
The quantity you're constraining.
This is sorry, I'm gonna go to more.
No, it's okay. We're not discussing.
It's about sigma 8. There's this sigma 8 tension. So people are thinking it's linked to the fact that the gas is expelled out. And therefore there's a matter power suppression, maybe by variance, but that's actually an open question, and that's what we're trying to understand right now. Okay. But great questions. Actually, many of them I don't know the answers, and I'm actually interested in understanding them. So, okay, as I told you, we're planning to constrain, what I was saying? Velocity reconstruction for KSZ. Great. So we had different questions, and one of the questions we had was, well, how good are we on this? So here I'm showing a 2D histogram in which the horizontal axis corresponds to the true velocity along the line of sight of galaxies with respect to the reconstructed velocity. And this is a 2D histogram, and you might say, well, it doesn't look that good. Well, just for you to know, this is a logarithm histogram, so it's actually, most of the galaxies are in here, but there's some galaxies over here. So if you have a perfect correlated result, all of these galaxies will rely here, where the line where all the estimated velocities correspond to the true velocities. But what happened is that we have, for example, galaxies that we know that the true velocity, let's say, is 1,000 kilometers per second, moving away from you. Yes, moving away from you. But when you estimate them, it's almost zero, or some of them are even, sorry, let's see here. Okay, let's see this point. So here, okay, you're estimating there's a galaxy with 1,000 kilometers per second moving away from you, but when you estimate their velocities, you're getting negative velocities. So why are we having these weird effects that some of them, we're estimating them in a different direction? Well, the answer is that if you see the way we populated galaxies is that if you have a big halo, you put a central galaxy, and you might have a satellite. We're using galaxies that look like the DESI galaxies, in particular the light luminous red galaxies, the big luminous red galaxies. And you will put a central galaxy, and this is the dark matter halo, and you might have a central, and usually, sorry, a satellite. And usually satellites have higher velocities, they have viral motions, and therefore, because of redshift space distortions, if you're looking from the left in here, you might see displaced because of this effect. So, as I said, satellites have peculiar velocities, they might also have higher redshift space distortions. So when you see them in redshift space, they will be shifted. And therefore, when you do your estimation of the field, of the velocity field, you will end up estimating a velocity of the opposite position on the infalling over density. And that would explain why we have these weird cases that they are uncorrelated. And the question is, is there any way we can actually overcome that? Going back to your question, if we assume that the gas follows the dark matter halo, instead of thinking on the velocities from the galaxies, we can try to think of the velocities of the dark matter halo. So in here, I'm showing the same plot, but instead of plotting the true velocities of galaxies, I can plot the true velocities of the host halos. And immediately that effect decreases, and the correlation coefficient increases from 0.55 to 0.73. So in other words, we're better constraining the host halo velocities, which makes sense because they do not have these redshift space distortions. And if our assumption is, which is approximately correct, gas follows galaxies, and sorry, gas follows the dark matter halos, this is great news for KSZ because, as I said, the signal to noise is proportional to R, correlation coefficient. So this is convenient actually for the KSZ because immediately we're more sure that our signal to noise is better. Another key result is the following. So we were exploring different things. So what happened if we have our box and we took out some galaxies and we decreased the number density? How this method will get worse. So in here, I'm showing you the number density and the correlation coefficient parameter. And if we start here and then we decrease the number density, it's almost flat until a certain number. So if you see this in this GIF, you will see that when we decrease the number density, or increase in this case, the large structure information is not missed. The good thing is that given that our method reconstructs the large scales, smaller scales are loose, but given that we have still enough number density to constrain the large scale, we're good at reconstructing them anyways. In other words, you need less galaxies than maybe you would expect to get a decent signal to noise measurement. So instead of having a more dense sample of galaxies, you can have a wider and explore different parts of the large constructor. And this is good for survey planning because if you have a lot of money and you can decide where to look in your telescope, well, you can say, hey, if you actually point to many parts, you can get this kind of science. So this is good for survey planning. And I'm gonna go to there are many results from this paper, but because of time, I'm gonna go to in my personal opinion, the most relevant, which is, okay, so when we have this box, we know the 3D location of galaxies because it's a simulation. If you have a spectroscopic sample, this is almost the same. You have the 3D position. But what would happen if you consider, let's say, photometric sample? In other words, you start to miss the information of the galaxies along the line of sight or the position. So what we did was to add noise on the position along the line of sight with this photo C uncertainty. So we add Gaussian noise. There are more different ways of doing this and better techniques, but in average works well. So what we find here was when we increase the photo C uncertainty or the noise of my sample, the correlation coefficient, of course, will go down. So in other words, if you miss some of the dimensions, and in particular the one along the line of sight, your reconstruction gets worse and worse. And in other words, that would give you uncertainty of the position of each of your galaxies. But good news, for LSST regime over Rubin, for the goal of the photo C uncertainty, the correlation coefficient goes from, let's say, 0.7 to 0.35. If you think of that, that corresponds to more or less a factor of 2 degradation on your signal to noise. But usually, galaxy surveys with photometric data have way, way, way more galaxies. So you can actually make it up, the signal to noise ratio, with the number of galaxies you actually have. In other words, you can maybe get the same signal to noise using more galaxies, but from a photometric sample, than a spectroscopic sample that might have less. So we were actually shocked because people never thought that this was something you could do with, photometric galaxies. But it's mainly because these scales that you lose the information or the uncertainty on the position along the line of sight, it's bigger than it's smaller than the larger scales that you are actually reconstructing with this formula of the linear continuity equation. So we were like, let's do it. Let's use this and let's see if we can actually get a signal for the first time. And we did it. So we went to the most state-of-the-art surveys available in the market. So we used DESI photometric galaxies. So before you start pointing your spectroscopic experiment, you need to know where galaxies are. So you have actually a photometric catalog. And in DESI, they use a combination of 3 surveys. So DECALS, DES, and this one that I don't know how to pronounce, that had a lot of galaxies, and we combined them with the latest maps of the CMB. And I'm not gonna, because of time, I'm gonna jump this. It's details on how we detect this, but I want to show you the result. So you can measure the profile of this gas, but instead of measuring the profile itself, we measure something similar to a cumulative profile. So here, we went to the CMB map, locate our galaxies, we had an estimate of the velocities, we stack. And when you do that with 6 million galaxies, almost 7 million from this sample, and then you see the cumulative profile of the gas, this is what you find. This is distance from the center of the galaxies or your cutout of the CMB map, and this is the KSE signal. What I want to highlight is that this is the signal we get in red. This is the highest signal to noise ratio we have ever detected with this technique, corresponds to 13.5 sigma rejection of the null hypothesis. We compared it with simulations and found an outstanding consistency with simulations that in particular have a lot of feedback out there, such as Illustrious. We also plotted the same profile but coming from dark matter. And what we find was a huge deviation. So here in orange, with respect to the red curve, we find that the gas is way more extended. And finally, because of the large number of galaxies and the redshift range, which was more or less from 0.4 to 1.1, we were able to understand this in an evolving universe, so for different epochs and redshifts, and also, for example, stellar mass estimates. And I invite you to, well, actually, I think I have some of those slides. So as I said, we have different redshift beams from photometry. And then we, for example, make this KSZ measurement, these profiles for different epochs of the universe. And we found, for example, differences that are still large. So probably with more galaxies, we're going to be able to understand much more the difference between these four beams. And finally, this is how the profiles look when you see the cutout, the final stacked cutout. But This is with a high pass filter, and that's why you don't see the large scale contribution. As I said, we also studied the evolution of these methods of these measurements with different stellar mass. And we find, for example, that much more massive galaxies do have a much higher KSE signal. And yeah, this is a stellar mass estimate. So galaxies with a stellar mass over 12 solar masses, actually, we had a great dependence, which is great. So in other words, we found that galaxies with higher stellar mass have more gas expended out, which makes sense. There's more stars, there's more activity, more things are happening out there. And I want to finish with saying that we have found, by studying velocity reconstruction in the context of KSE, great information. We still have a lot of questions to answer because this is one of the first times we have measured KSE coming from galaxies. What we find on these three works is that KSE is not only robust, but it's also great in photometric samples, not only in spectroscopic ones, which is the main result I showed you and my personal one, favorite one. And I'm currently leading the KSE measurement using the Atacama Cosmology Telescope, or ACT data, and the Dark Energy Spectroscopic Instrument, DESI, year 1 data with this method. So stay tuned to the archive because the paper is probably going to be pretty soon out there. I'm starting with collaboration review before we make it public. So thank you.
Thank you, Bernardita. We have maybe time for one question. I don't know if anyone. If not, I have a question. Okay, go.
I don't understand how you reconstruct the velocity using photometric information.
So what we did was the same equation, but okay, let me go back to the 4 steps. A great question. So when we convert from RA, DEC, and C coordinates to 3D, we add Gaussian noise on the redshift distribution. So you get like a noise along the line of sight, and then you just continue normally. And then you will get a worse estimate. But what we find for LSST, like forecast or expected noise, this is not that bad because, okay, let me go one back. No, sorry, one forward. So if you see this, the big blobs in here are more or less 200 megaparsec length. So let's say this is the big large scale velocity. And when you add noise, maybe you're adding this amount of noise. So you're not actually losing the large scale information. You're only smearing it a bit, but it's still inside of the large scale. And that's why in this figure, that one, once you start adding it, you still can see some of the large scale distribution because you're adding noise, but still inside. So yeah, it's worse, but it's not, we find out that it's not that bad.
Okay. Thank you again, Bernardita. Let's give a round of applause.
I also have half an hour before a meeting, so if anyone wants to discuss about this, I'm happy to chat. Yes.